Okay, so in this tutorial, we're going to utilize the surface that we created in part one. Actually, we're not going to utilize the surface itself, but we're going to use a lot of the same information. So make sure you have this script kind of put together as a starting point. I want to go back to way back here where we originally subdivided our surface. And you can see, if you remember, we made a bunch of points and we made a bunch of normal vectors, but we're not using this other output, which is the actual UV parameter, or the location, the parameter location of each one of those control points on our original surface. Now, what I want to do is actually go to Surface, Analysis, Evaluate Surface. Okay, and this guy, and we actually used this before with the MD slider, but this guy uses a coordinate on a surface, and it draws an object, or I'm sorry, it gives us a bunch of information based on where that coordinate is. So if I plug this surface into our original surface back there, ready, and then we plug our UV or our parameter coordinate in, you can see now we're not just getting, this basically just gives us more information. So we have not just the point and the normal vector, we also have a UV direction, and importantly, we have a frame or a kind of a construction plane. You can see there's a bunch of these in. So now at each one of those points, it's making like a little kind of XY coordinate plane. And this is something that's used a lot in Grasshopper, like kind of local orientation space or local, Cartesian coordinate space, just to, kind of deal with more complex surfaces and stuff like that. And what's cool about this, for example, is if we went to our curve tab and go to primitive, there's a component called circle. We can also draw polygons, rectangle, or a pentagon or something. We're just going to get this component that's called circle. So way back when, we want to use those frames that I just described as the kind of planes that define the orientation of each of these circles. So it's asking me for a plane. That actually means the same thing as a frame, which we're getting out of our evaluate here. And if I plug that into plane, you can see it's now creating a circle around every single one of those little faces. And I can also set the radius here, so that defines obviously the circle, number slider. And now based on that number slider, the size of each one of those changes. Now, if you remember as well, we were using earlier these kind of, or this closest point component to derive like kind of distance values for each one of these points on the surface relative to its attractor or its closest attractor. So we can actually do the same thing rather than using it to move the points and regenerate a surface. We can use that to set the radius of each circle. So what I'm going to do here is actually flatten my frames, or I can also go way back to my surface divide, right click on the output and go to flatten, because we don't want to combine a list of values that's unflattened with a list of values that is flattened. Actually, let me just show you what that will do. Get a understanding of why. So basically for every single value in our remap, it's going to combine that with every single frame. You can see it's applying every single radius value to each frame, not what we want to do. So if we then went back to our UV and flattened that, see now that it's making a single circle around each point. And once again, the domain that controls the target domain that controls our remap is how we would adjust that. So the lower number adjusts the size of the circles that are further from each attractor point. The higher number adjusts the circles closer to each attractor point. I'm actually just going to disable this for right now. But now I could go back and divide my surface more. And you can see, obviously, it's not going to change. Yeah, actually, we could actually drive that sort of parametrically, but I'm not going to do that for decimal. Oh. And we also want to kind of have it subdivided even. There we go. And then if I unpreview those points once again, see we get this kind of pattern of larger and smaller circles that are being driven by their proximity to these attractor. Move them in and out. I'll change what each circle does. More variation. So we can apply the same principle to really any geometry, right? If we were to parametrically model our geometry, rather than just okay, sorry about that. But as I was saying, if we were to parametrically model, for example, like the surface or something simpler, we could actually change how that the kind of structure of that geometry is working based on an attractor point or something like that. So I'm actually going to demonstrate that as well right now really quick. So I will go back to where I created the original surface. And I'll just redo this. You guys didn't watch two. So in order to subdivide a single surface into multiples and in order to subdivide a surface into multiple subsurfaces, what we also want to do is use something called isotrim. So if I go to surface, first of all, analysis, or I'm sorry, utility is a component called isotrim. And this thing requires a surface, an input surface that it wants to subdivide, and a domain of the subset. In other words, how it wants it to be subdivided. If you're interested in what that actually means, there's more explanation on that in video number 2. But for now, we'll just go to math, go to domain. We're going to get a component called divide domain 2. And I'll plug my surface directly into the I, or the base domain input for that. And then I'll plug these two number sliders into UV. And that will automatically create the type of data we need to subdivide this surface into smaller surfaces. Grid. And you can see, like we did with our point divide before, the number of subdivisions in direction changes how many subsurfaces in direction. Excuse me. So that's our starting point. Now, we're also going to use that deconstruct brep like we did before under surface. Under analysis, there's a component called deconstruct brep. It looks like a cylinder with an explosion around it. And I can take, so right now this is outputting, and if I hover over the output, giving me individual surfaces. So each one of these is actually now its own separate subsurface or own surface. And if I plug that into my deconstruct brep, it's kind of breaking it up into more information. So first of all, it's giving me the faces, just the surface itself, giving me the edges, so the curves that define the outside edges of each, and then the vertices. So if I start from there, I'm actually going to also then get an evaluate surface. So I'll go under analysis, go to evaluate surface, and I'll plug the faces or the surface into S. I'm also going to right click on that input and go to reparameterize so I can use a coordinate between 0, 1. And then I'll go back to parameters, input, and get an MD slider, like a two-dimensional coordinate slider. Okay, and now we're finding the center point of each of our subsurfaces. That's why we have all these crazy planes. And if I get a vector display component, again, just type in vector display, but this is just so we can kind of preview what's going on. And I'll plug my points, or PA, normal into V. Now we can see we have a little localized vector that is perpendicular to the surface at each center point. And again, this is actually dependent on original setup where we morph the surface based on vector points. See those arrows kind of changing direction and shape. So now what I could do is I could actually reposition the points. So also, if I re-preview this component, you can see it giving us a little orientation plane. And if you remember before, we actually drew a bunch of circles on those planes. And I'm going to do the same thing now. So I'll go to curve, primitive, circle. And I'll draw a circle around each frame once again. And this time I'll actually make a separate copy paste this whole, the remap, the bounds, and the domain. Plug that into the radius. Flatten. I'm sorry, actually I can't do that. What I need to do is need to kind of redefine this. You're going to copy this. All right, so just go back a few steps. I'm going to copy this and these attractor points, or not the attractor. And I'll just drag that and tap Alt or hit Control C, V. And so now we actually need to use, because basically what happened is we subdivided our surface again right here. And so now we use different numbers to subdivide it this time than before. And so it doesn't have the same number of points. So it's not interpreting for the radii of the circle. So all we need to do to fix that is, again, use our center points from our evaluate surface and plug those into P. C remains the same. That's our original attractor points. And then all this stuff can remain the same. I'm going to flatten my bounds because I want to know the bounds of the whole list, not just branch. Right click on the N input, flatten it. Now if I plug that into radius, I think it's giving me too many numbers. Oh, because I flattened this. That needs to be not flattened. Just right click on untoggle the flatten. And then I'll unpreview that evaluate surface. Kind of okay, cool. And then what I want to do is move each of those circles. Now, I could move the circle itself. Actually, that is what I'm going to do. I'm going to move the circle itself. Again, I'll just go to transform, go to Euclidean, and I'll get a move component. If you remember from part 1, this requires a geometry, which is our circle, and a vector, which is, again, that's going to be the normal vector for each of our subsurfaces. And to modify the length of that movement, again, I'll go to vector, I'll go to vector and amplitude, and plug the normals into that. And once again, this time I'll just copy these 3 components. And I move vectors, or I'm sorry, move the circles based on a proximity to vector points. convert it here. Okay, and so now you can see we have another set of circles that are also being kind of parametrically driven, the size of them and their distance from the original circle. And now I can make a geometry from this. So I'm going to use the edges from each individual subdivided surface, and I'm going to loft them to the circle. So I can just get first I want to get a join curves component. Type in join. Also go to curve and I believe utility. I'll plug my E from my deconstruct brep into that, into C. So now we should have one outline. Like by default, that's 4 separate curves for each subsurface. And now it'll join them into one closed curve. Then we just loft the two together. Again, this is one reason we would want to have branches in our list, because it'll know that we just want to loft that one to that circle and that square to that circle and that circle, rather than loft everything in one giant sequence. Really destroy our computers. So we'll go to surface, freeform, and get a loft component. And like I mentioned before, if I click and drag one of these curves in, then I can hold shift to click and drag the other one. First of all, it's not working. So this is because of, again, every time we or sometimes when we add a component, the number of paths that define our branches will change. So see that this list has individual paths, and like this address has 3 values and this address has 4. So it doesn't know how to match them up. And the reason that happens is sometimes when you use a component, it'll just add a branch. Add a branch, even though it's not really doing anything because everything's already in its own branch, right? Basically, a simple way to fix this problem when you see that you have 2 like different length paths for each branch is we just right-click on the component and we hit simplify. And it'll remove every number that's not making a separate branch. Do that for both of these components. And then you can see it's already started to our surfaces. Now, the other thing that's happening here is the rotation of our circles is a little bit off of the rotation of our original squares. That's why it's making this kind of puckered, or this kind of like twisted shape in between the original circle and the square. That's actually pretty easy to do. Well, what we need to do is just rotate the planes that each of the circles are drawn on originally. And what's nice about that is if we double click and type in rotate plane, we want that specific one that says rotate plane. Because a plane already has its own orientation, we can use this component just to rotate it around its own z axis. So we'll plug the planes into that, and then we need a rotation value, our a, that's a number. And Grasshopper uses radians, but we can convert degrees to radians by using a radians component. So radians, that component. And then I'll make a number slider that's like 180. That into P. Now you can see as I move the slider, so that's 90, that's 1, etc. So I'll replace those planes, draw the circles. Then as I rotate the guy, looks like it's, oh wait, is it? Yes. There we go. Now we have circles that are more closely aligned to squares that they're lofted to, and I'll unprefix planes and see what. Okay. So so now it's really just a game of kind of tuning our want the ones that are further to move further. No opening. But in other words, we have a single geometry, right? It's basically just a square lofted to a circle, but its whole kind of the whole way that you model it is being parametrically driven. So the size of each one of these squares, its location on the surface, the size of each one of these circles, its distance from the original square, everything, every like part of this geometry is being parametrically or being driven by a parametric set of numbers. So we can get it to be kind of highly varied. And take this guy. There we go. Add that one to. Okay. And I wonder, the ground plane. There we go. Now we get some. And oops. Just way. Okay, so now you can see that kind of based on these geometries, they would all actually start to. They would all sort of start to produce specific or specific light and patterns of light and shadow, specifically based on how they're morphed. So I think one approach to this is sort of like saying the way that the surface is morphed has to do with like how we want to kind of provide light or modulate light. So that's the whole kind of end goal of this type of modeling. So with that, I sign off, and that will conclude this series of tutorials. All right.